This ancient water system, carved into the desert of southern Peru over 1,500 years ago, still delivers free drinking water to 30,000 people today. No electricity, no pump, no filter, no chemical treatment. The Nazca people dug spiraling stone funnels into the earth, some as wide as 15 meters across, descending 10 to 15 meters below the surface to reach underground aqueducts lined with smooth river cobble. Spiral geometry is not decorative. It is a wind-driven pressure engine, funneling prevailing desert gusts downward into the tunnels and forcing water through a gravity-fed network of channels and reservoirs across one of the driest landscapes on the planet, where annual rainfall averages less than 25 millimeters. 43 of these systems were still functioning as recently as the year 2000. Yet in June of 2025, engineers at the Massachusetts Institute of Technology published a paper in the journal Nature Water celebrating a window-sized panel that produced 161 milliliters of water per day, roughly 2/3 of a cup from air in Death Valley. So how did a civilization with no written language and no metal tools outperform an MIT laboratory by a factor of thousands? What happened to this knowledge in the 15 centuries between then and now? And why does no modern building code on Earth reference a technology that still works today? Let's find out. To understand the Nazca spirals, you have to go back at least 2,500 years and across an ocean to the Iranian plateau. Beginning around 1000 BCE, Persian engineers developed the qanat, a gravity-fed subterranean aqueduct that tapped alluvial aquifers at the heads of mountain valleys and channeled the water through gently sloping tunnels, sometimes stretching over 45 kilometers, to settlements on the arid plains below. The qanat at Gonabad in northeastern Iran, built between 700 and 500 BCE, still provides drinking and agricultural water to nearly 40,000 people today. Its mother well descends more than 360 meters below the surface. By the time of the Achaemenid Empire, Persian rulers were granting 5 generations of tax exemption to anyone who successfully constructed a new qanat. The technology spread westward along trade routes into Egypt, across North Africa into what the Romans called Fogra, and eastward along the Silk Road into Afghanistan, Pakistan, and western China, where the Turpan water system sustains agriculture in the Taklamakan Desert to this day. In 2016, UNESCO inscribed 11 Persian qanats as a World Heritage Site, citing them as an outstanding example of a technological ensemble illustrating significant stages in the history of human occupation of arid and semi-arid regions. Different continents, different languages, different tools, the same physics. But perhaps the most remarkable iteration of this underground water principle appeared not in the Old World, but in the valleys of the Rio Grande de Nazca in southern Peru, sometime around 500 CE, during what archaeologists call the Middle Nazca period, the Nazca civilization, which flourished from roughly 100 BCE to 800 CE, constructed a hydraulic network so sophisticated that it sustained an estimated 25,000 people across dozens of villages in a region where rivers ran dry for most of the year, and precipitation barely reached 1 inch annually. The system is called the puquios, from the Quechua word puquio, meaning spring or source. And the defining feature of the Nazca puquios is the spiral, a corkscrewing funnel of dry, stacked riverstone that descends from the desert surface down to the underground channel below. To understand why the spiral matters, you have to understand 2 physical principles working in concert. The first is the Venturi effect, named after Italian physicist Giovanni Battista Venturi, though the Nazca applied it 15 centuries before he described it. When a moving fluid, in this case wind, is forced through a narrowing passage, its velocity increases and its static pressure drops. The spiral ojo, or eye, narrows as it descends. Prevailing winds blowing across the desert plain are caught at the wide mouth and accelerated downward through the tightening coil. This creates a pressure differential at the base of the spiral that effectively pushes air into the underground tunnel. The second principle is the Bernoulli effect on the water itself. As the pressurized airstream enters the underground channel, it exerts force on the water surface, propelling it along the gently sloped aqueduct toward the open trenches and collection reservoirs called coches downstream. The spiral is not a well. It is not a maintenance shaft. It is a wind-driven pump, possibly the first wind-driven pump for moving water at this scale in the history of the planet. Rosa La Saponara of Italy's Institute of Methodologies for Environmental Analysis, in cooperation with archaeologist Giuseppe Orefici, confirmed this function using satellite imagery and multispectral analysis, published in 2016. Her team demonstrated that the ojos funneled wind into the underground canals, and that the system was once far more extensive than the surviving 43 aqueducts suggest. Archaeological evidence confirmed that Nazca settlements would not have been habitable during the Nazca period without this hydraulic network, and the performance of these systems is not anecdotal. It is backed by 15 centuries of continuous operation. The Cantalic aqueducts, located just 4 kilometers from the modern city of Nazca, remain the best preserved and most visited section of the network. The underground galleries extend 10 to 15 meters below the surface, with tunnel dimensions of approximately 1 meter square. The ojos are spaced 10 to 30 meters apart along the channel, their funnel-shaped openings sometimes reaching 15 meters across at the surface, but narrowing to just 1 to 2 meters at the base. The longest single gallery section stretches 372 meters underground. The open trenches downstream can extend over a kilometer, lined with smooth river cobbles in a V-shaped cross-section that slows water velocity and prevents erosion. No mortar, no concrete, no imported material. Every component sourced from the local terrain. But water harvesting from the atmosphere is only one benefit of these passive systems. Across the Atacama Desert in neighboring Chile, indigenous communities developed their own parallel tradition. For centuries, people in the arid northern coast hung animal skins to catch droplets from the Camachaca, a dense coastal fog composed of microscopic droplets between 1 and 40 microns wide that rolls inland from the cold Humboldt Current. In the 1950s, a physics student at the University of Chile named Carlos Espinosa began modernizing this ancient practice, building brass frames with nylon mesh sheets to collect condensation at scale. His prototypes became the foundation for Chile's modern fog catchers, or atrapanieblas, which now produce over 2,000 gallons of water per day in the village of Peña Blanca alone. Chilean researchers at the Pontifical Catholic University of Chile estimate that capturing just 4% of the water contained in the Atacama's fog banks would meet the needs of every community across the entire desert. In Morocco, the Darcy Mod organization installed 600 square meters of fog, trapping nets atop Mount Boutmezguida in the Anti-Atlas Mountains, using Cloudfisher technology designed by German industrial engineer Peter Trautwein. The system captures an average of 6,300 liters of water per day, enough to supply 16 villages and over 1,000 inhabitants at an altitude of 1,225 meters. The project won the United Nations Momentum for Change Climate Change Award in 2016. No compressor, no desalination membrane, no electricity bill, just mesh, wind, and physics that predate every utility company on Earth. So why, given millennia of proof across 4 continents, has atmospheric water harvesting remained invisible to the modern construction and water industries? Follow the money and the picture sharpens. The global bottled water market was valued at approximately $354 billion in 2025. That figure represents one of the largest consumer product categories on the planet. Nestlé, PepsiCo, the Coca-Cola Company, and Danone dominate the sector. A passive water system that produces free drinking water from wind, fog, or subterranean aquifers using materials that cost nothing represents a direct threat to that revenue stream. A puquio that lasts 1,500 years is a single transaction. A bottled water subscription that lasts a lifetime is worth thousands. But the market alone does not explain the absence. The regulatory architecture does. Modern building codes in the United States, governed by the International Residential Code, reference water supply almost exclusively through municipal connections or drilled wells. The IRC does not contain a single provision for passive atmospheric water harvesting, fog collection infrastructure, or wind-driven subterranean aqueducts. The American Water Works Association, which sets distribution standards adopted by municipalities nationwide, defines potable water supply in terms of treatment plants, distribution mains, and metered service connections. A system with no meter, no treatment chemical, and no recurring service fee does not exist within this regulatory vocabulary. It is not banned, it is simply unrecognized, which in practice functions as a de facto ban through bureaucracy. Homeowners in many jurisdictions cannot receive a certificate of occupancy without a code-compliant water supply, which means a municipal hookup or a permitted well. A system that harvests water from fog, wind, or shallow aquifers through passive stone channels does not qualify, regardless of the fact that it has been producing safe drinking water for over 1,000 years. The industry decided that simplicity was not profitable enough. Meanwhile, the MIT Atmospheric Water Harvesting Window, published in Nature Water in June of 2025 by Professor Xuanhe Zhao and lead author Chang Liu, produced between 57 and 161.5 milliliters of water per day during a week-long test in Death Valley across humidity levels from 21 to 88%. The device uses a lithium chloride-infused hydrogel shaped into a dome-patterned origami array resembling bubble wrap, sandwiched between two glass sheets coated with a radiative cooling film. Water vapor absorbs into the hydrogel at night, then evaporates and condenses on the glass panels as temperature rises during the day, trickling into a collection tube. The team reported lithium ion concentrations below 0.06 parts per million in the collected water, which falls below the United States Geological Survey safety threshold. The hydrogel retained approximately 90% of its capacity after 340 cycles, equivalent to roughly 1 year of daily operation. It is a remarkable engineering achievement, but the manufacturer claims 161 milliliters per day. Although independent peer-reviewed assessments of similar sorbent-based systems produce more conservative figures, typically in the range of 0.1 to 0.8 liters per square meter per day. A single Nazca puquio, by comparison, delivered continuous year-round water supply to an entire agricultural village. If you want to integrate passive water harvesting into your own property, here is what that looks like in practice. The first step is a site assessment. Determine your annual fog frequency, prevailing wind patterns, and whether a shallow water table exists on or near your property. In coastal or mountainous regions with regular fog events, mesh fog collectors are the most accessible entry point. A standard fog collector, a 1 square meter polypropylene mesh sheet mounted vertically on 2 poles, can produce between 2 and 8 liters of water per day, depending on fog density and wind speed. The Cloudfisher system, manufactured by the German Wasserstiftung Water Foundation, uses a reinforced polyethylene mesh rated to withstand winds up to 120 kilometers per hour. A single large format Cloudfisher net, approximately 12 square meters, costs between $1,500 and $3,000 installed, and can produce up to 600 liters per day under optimal conditions. For regions with low humidity and no fog, the sorbent-based approach demonstrated by MIT is a viable path, though currently at prototype scale. The hydrogel formula uses polyvinyl alcohol as the base polymer, lithium chloride as the hygroscopic salt, and glycerol as a stabilizer. The origami dome array maximizes surface area. All components are commercially available. The team at Zhao Lab at MIT has published complete material specifications in their Nature Water paper. For those with access to a shallow water table and land with adequate slope, the qanat and puquio model remains the most durable option, though it requires geotechnical survey, an understanding of local aquifer depth and flow direction, and significant manual labor. Companies specializing in permaculture earthworks and water harvesting design, such as Watershed Management Group in Tucson, Arizona, offer residential consulting and workshops starting at approximately $300 to $500. A critical warning: do not confuse cheap imported fog nets with engineered systems. Low-cost mesh without proper filament diameter, hydrophilic coating, and structural framing will degrade rapidly in UV exposure and high wind conditions, producing negligible water and creating a maintenance burden. Because there are no moving parts, no filters to replace, no compressors to service, and no chemical treatment required, the puquio and fog harvesting systems are effectively maintenance-free at the mechanical level. Annual checks should include inspection of net integrity for fog collectors, clearing of sediment or debris from collection channels and reservoirs, and verification that stone linings in qanat or puquio-style systems remain stable. The Nazca did this communally. The system ran for 15 centuries on social organization alone,